Today we are going to look at the aggregate. How are we going to use the aggregate root in domain-driven design for our coding work? So, what is an aggregate root? So, aggregate root can be called as a cluster of associated objects, or it's a group of associated objects. Um, and why do we need an aggregate root? It kind of binds all these entities together to achieve its purpose. Uh, I think it's best to explain with examples what is an aggregate root, and it's always should treated as a single unit of for data changes. So any data changes for anything inside the aggregate root should happen inside via the aggregate root. So let's say some examples. If you see an example of e-commerce, uh, if you see the order, order can have many entities related to it, and the order item is an entity, and the address. Any changes to these entities should go through the uh, aggregate root. So aggregate root here is the order. Okay, so there can be many sequence of actions that's happening. Can be something, can be status can be changed, some data can be changed, but everything should happen within or via the aggregate root. That's the whole concept. And here the order is the aggregate root, and all modifications to order item or address must go through the order. The entire aggregate is loaded, saved together. So whatever that happens will happen atomically together. Another example we'll take is the blog posts with comments. Here we have the blog post and the comments entity, uh, and it has many actions like add comment, remove comment, edit content, all these things, and related to the comments. Here, the blog post is the aggregate root, and comments can't exist without the blog post. So all comments operations managed through the post. This is another good example of why do we need an aggregate root. And another example is a bank accounting system. Bank account system. In the bank account system, we have the bank account and the transactions of a bank, and we can have a customers associated with the bank account as well. So here, bank account is the aggregate root. Transactions are value objects within the account. Balance is made consistent through the aggregate. So you can see how through the within the root aggregate there are multiple entities involved and the operations involved. Flight booking, another example. If you take the flight booking example, we'll have the flight booking, and there will be objects involved, passenger, seat assignment. All these objects will be there. The thing is, any change to these entities will happen through the flight booking aggregate, root aggregate. Um, uh, all passengers and seat operations go through the booking. There's so whatever changes to these entities will happen through flight booking, root aggregate. So, and the root aggregate ensures no duplicate seat assignments here. So this kind of business logic happens through the aggregate. It makes sure it is consistent. So now we had some examples about aggregate root, and we'll see the advantages. We'll kind of revise it. So it's kind of an entry point. So whenever that you want to do a particular series of actions, particular transaction, then the entry point is the aggregate root. So we don't go inside the related objects one by one and do. We go directly to the aggregate root as the entry point. So that's my end point. It's the only object in the aggregate that outside objects can hold reference to. So outside access is to the aggregate root. Consistency boundary, it ensures the aggregate is always in a valid state. there can be many state changes. For example, if you put an order, shipping status can change, payment status can change. So it the aggregate's responsible to keep the status consistent across the whole flow. And transaction boundary changes within the aggregate are typically made atomically. So the aggregate transaction, the flow happens is kind of a atomic, basically uh, succeed together or fail together concept. So we looked at certain examples, and and why so one of the things that that aggregate helps to do is it helps with maintaining invariance. Invariance means maintaining business rules and inconsistencies. So in an aggregate, there can be many invariants such as or business rules or constraints rules that we need to follow. For example, if you placed an order, it's just to make sure that it's in the shipped state. It's not in the ship state. The order cannot be ship state when you try to modify it, and also the quantity cannot be less than one when the order is placed. It doesn't make sense. And the total order should be equal to the number of order lines, sum of order lines quantity. So these are perfect examples of invariants, we can call business rules or constraints. It also provides kind of a transactional consistency, meaning that invariance can when we go in a transactional flow, it can validate certain things, whether the transfer, let's say in this example in bank account, when you do a transfer, if it is it more than zero, it can't be negative amounts, balance should not be zero to do a transaction, all that stuff, and call other services as well. And it's mainly atomic as well. So as I told earlier, either it needs to succeed as a transaction or fail and roll back accordingly. um, so there can be mainly four types of invariants or business rules or constraints. One is structural, meaning that one entity should have one or many related entities. That's one structure. Example of a structural invariant. So value invariant is basically our account should have more than or a positive value. And temporal is once the order is shipped, it cannot be modified. This checking the status or something like that. And cross-entity variance, meaning that uh, that involves multiple entities. For example, the total uh, quantity should be kind of or the total value price should be equal to the sum of all prices stated for the order lines. Um, Other than that, let's say one of the important thing about aggregate or preferred, we can't say it's a hard and fast rule, but the preferred way of handling with aggregate roots is using a reference. Um, so let's say there is one aggregate root called A and another aggregate root called B. So from A, if we are trying to use B, we would not hold the entire B object in our A aggregate root. Instead of, we will have a reference. So the perfect example is this. Let's say if we take the order class, if we are holding this entire entity here direct reference to another aggregate, this is wrong. So we are having those entire thing inside, that something that we don't want. What we instead want is the reference only. So custom ID, there are a lot of benefits because in a DDD domain driven design architecture, we try to separate the domains, right? So order is a different domain, customer is a different domain. So when we try to put everything together, does it make sense? The object, the whole aggregate becomes complex, unnecessarily complex, and it's supposed to do only what it's supposed to do. So order we have, and we are only having the reference for the customer. So whenever that we need, what we can do is using this customer ID, we can call the repository of customer, which is from a different domain, and we can get that information and work with it. Simple as that. So another example is a medical record. If we take, then we have the reference of other aggregates, a patient ID, doctor ID. So we don't unnecessarily make it complex by keeping the entire object here, which you don't want. And I think it really helps with the performance as well. So when we have the nickel record, we don't really necessarily have all this information. Whenever that we need, we will refer this. um, yeah, so this is what I just explained. So whenever that when I need the information from different aggregate, we call them by the ID and we take them. um, so when validation also, we can call them their own aggregate functions and we can validate. We don't do it in our aggregate is everything. So it gives clear separation of domain. So each domain is responsible for its own bounded context to maintain its business logic. um, so there can be exceptions, of course. As I said, it's not a hard and fast rule. So when we need to do optimizations, we will there can be performance critical or scenario critical situations where we need to change this rule a bit. So in that case, there can be exceptions. So but the benefits of this approach, to summarize again, is you can have clear boundaries. So each aggregate manages its own consistency and better scalable, reduce database locking needs. So each of them domain responsible for their own uh, thing, so that we don't necessarily maintain the locking of databases. And simple transaction, it makes things simple instead of complex, and more flexible architecture across distributed services. um, so yeah, it promotes loose coupling, and it also brings another important subtopic, which is eventual consistency. So this is an example of a product inventory. uh, Here what it does is, let's say an order is placed. Once an order is placed, there can be many things happening, right? You need to place the order, and inventory needs to get updated, payment needs to be succeed, and shipping needs to be placed. So once, let's say, payment is completed, there should be an event coming back to the product inventory to reduce the stock, something like that. So this is will come in an event form. uh, so meaning that it's not a strong consistency. That means we are not, everything is asynchronous. Everything is subscribed for an event and waiting for an event. So when we do an e-commerce transaction, it takes time. It may have uh, immediate or temporary inconsistency, but eventually it's supposed to resolve itself. So that's the whole meaning behind eventual consistency. uh, so these are the some important things behind aggregate root concept. So we talk about eventual consistency, and let's talk a little bit about cost aggregate queries. So this is very so if you talk about cross aggregate queries and transactional upgrades in this context is uh, when in microservices or DDD architecture, data is partitioned across different aggregate services. Okay, so querying data that spans multiple aggregate is challenging because no single database. There can be multiple databases across multiple domains. Then multiple calls to multiple services can be expensive. Multiple API calls, uh, and all those services doesn't necessarily need to have single database technology. Someone can use SQL or can use Oracle, something like that. So this can bring some complications. So one of the things that we can do to solve this problem is API composition. Query makes multiple services, request to multiple services, combine these results in memory. It's simple to implement, but multiple network calls again joins done in the application code. So this is not that good. So another way to do this is CQRS read models. Basically, if you know the CQRS model, what we can do there is a way of implementing is basically we maintain the read model separately and the write model separately. So whole key point there is uh, the base point there is basically the reads are faster and the writes are slower comparatively in a database, so we keep those two separately. And um, uh, so reads can be really fast. We can take very strong consistency. We can take the reads in a faster way. uh, Meanwhile the writes will happen slowly, leisurely, where eventual consistency is provided. It will eventually be updated in the relevant write databases. So there can be two separate databases there are maintained. Uh, so the idea there is this can be optimized. The read model can be optimized to temporarily to combine pre-combine things and to make things very efficient. So the read tables are optimized, um, so that it will work really well with aggregates. The another thing when it comes to transactional updates across aggregates is when you talk about transactions. One of the way to do is using sagas. So saga is basically kind of a managing a transaction internally. So what happens is an example of a saga is it begins an let's say order is placed. So it begins a order saga. So it reserves inventory and its process payment. It if payment fails, execute compensating actions to unreserve the inventory. So success together or fail together concept. So so again, talking back about Saga is a design pattern for managing distributed transactions in microservice architecture, where a single business operation spans multiple services, each with its own database, possibly can be in one ways. Unlike traditional systems, Saga breaks the operation into sequence of local transactions coordinated through events or commands. Okay, so basically, Saga is one thing and it has a sequence. So each sequence will have can emit an event which will eventually get consistent. So it the whole idea or the point with sagas is it becomes kind of a transactional scope. Um, so there can be two types of sagas. One is choreography based on event driven, such as that we use a broker, Kafka, or RabbitMQ, and each service listens to it for events and reacts accordingly. So that's one way of doing these things. And orchestration based saga, centralized control. Saga orchestrator is there, so it orchestrates and controls where the events need to be fired and which actions need to be triggered. So this is in nutshell what we need to talk about aggregate root. We'll further dive into other subjects when necessary. Thank you for listening today.